far we've talked about figuring out what omega is, that is figuring out what the angular velocity is, more from a sort of thinking about how things are moving and sort of doing some fairly simple calculations. I'd like us now to sort of pull out our vector analysis guns a little bit to try to come up with a more generalized expression for what the angular velocity of a particle is. Okay, and we'll do that first in polar to think about how that works out, and then we'll generalize that polar result. Okay, so let's think about some general situation. Right, we've got some object that's located at some position r, right, and it's moving at some velocity v. And now, if I use polar coordinates to describe this, I would say the position vector as a function of time is r times r hat, and the velocity vector as a function of time. If this object is moving in some direction that's not purely radial, the velocity vector is going to have terms that both depend on how the distance from the origin changes in time and how the unit vector r changes in time. In other words, how the angle theta changes in time. So in this case, we've done this before. The velocity vector is going to be r dot times r hat plus r theta dot times theta hat. Okay? Now let's take a minute to think about what this means from a sort of angular velocity perspective by decomposing the velocity into two parts, right? One part of this velocity is the part that is going away from the origin, right? This is motion away from the origin. And notice that that part of the motion doesn't result in any change in theta, right? I mean, if it were only moving away from the origin, if just r were changing and theta were not changing, this term would be 0, this term would be non-zero, the object would be moving straight away from the origin, and in that case, the angular velocity would be 0. So this motion away from the origin does not contribute to the angular velocity. Okay. On the other hand, let's think about this second term. The second term is the component of the motion, the velocity, which is perpendicular to the direction away from the origin, right? So you have this sort of motion that's in the r hat direction, so this is the sort of radial component, and then this is the motion that is perpendicular to the radial component or in the theta hat direction, right? So this is motion perpendicular to the radial direction. And it's this motion that causes there to be an angular velocity. This is the motion that yields or corresponds to an angular velocity. Okay, so in some ways you could say, okay, if I want to figure out what the angular velocity is, I have to actually be able to pull out this part of the motion that is perpendicular to the radial direction. Well, if we want to pull out the part of a vector that's perpendicular to something, we have a couple of options. We can either pull out the dot product or the cross product. I'm going to pull out the cross product for this and say, okay, well, I know if I wanted to find v perpendicular, right, so the part of the motion that was perpendicular to the velocity or to the radial direction, I would say, okay, well, that must be my total velocity, right, and then I want to get rid of all the stuff that's parallel. So one thing I could do is cross that with r hat, or actually take r hat crossed with that. And the other thing I could do is I could take a dot product. Let's take the cross product approach. So I'm going to take r hat cross with v. And let's think about what that does. If I take r hat crossed with v, well, r hat cross r hat is 0, right? R hat cross theta hat is k hat, right? So for this polar coordinate case, this is going to be r times theta dot times k hat. Now, if I wanted to relate this to what the angular velocity is, I can see I've actually got the angular velocity in here, right? That is omega for this particular case. It's theta dot times k hat. So I could rearrange things and say, actually, omega is equal to r hat cross v divided by the magnitude of r, or another way of actually saying exactly the same thing is this is r cross v divided by the magnitude of r squared. And so certainly for the polar coordinate case, this is going to pull out the term theta dot times k hat, which is indeed the angular velocity vector here. But in fact, this expression is more general. It actually applies in 3 dimensions as well. Let's think about why that applies in 3 dimensions. If I think about some 3-dimensional case, I'll go to a new page. So here's a 3-dimensional case. I've got some object that is moving in some direction. Well, when it's moving in some direction, what I'd actually like to think about how I'd think about that from a rotational perspective is I'd say that object is moving in a plane, right? So I would think about what that plane was that the object was moving in. And then once I was thinking about that plane the object was moving in, I would ask the question, okay, for that plane that it's moving in, what's a normal vector that goes through the origin for that plane, right? So for example, if the object were moving in the xy plane, right? So here's so if this is x, this is y, and this is z. Boy, my pen is dying. Let me grab a new pen. And the object were confined to the xy plane, we're moving in the xy direction, then I can pretty clearly see that for that plane, right, this would be what the angle would be of interest. The object would be rotating would be moving about that z-axis in a counterclockwise direction, and so for that particular case, omega would be pointing out of the page, right? If I think, on the other hand, about an object that's moving in the xz plane, right? So here's the xz plane. So I've got some object that, say, is here, moving like that. That object, if I think about how that object is moving effectively counterclockwise about the y-axis, which is the sort of axis that is normal to the plane. So I would say that omega, for this particular case, was pointing up, right? And similarly, I could also think about an object that was moving in the yz plane. So say this object moving in this direction. Well, if I think about what that means from a rotational perspective, that object has an omega that is in the x direction, right? So for pretty much any object that I can think of, I can put that object into a plane. That plane that also goes to the origin, and I can ask the question, what's the sort of effective axis that object is rotating about? If I imagine, finally, one other example, let's imagine some object that's out here, moving in some direction. I can take that direction, right? And I can define a plane that includes that object and also includes the origin, and then start to think about, okay, what's the motion of that object and what's the corresponding omega value? So now that I've sort of made that argument in the hand-waviest way possible, let's think about what that actually means for omega, right? For the angular velocity, well, for this case, right, we would take the object that's in the xy plane. We'd say, okay, there is r, there is v. Since r is in the xy plane and v is in the xy plane, r cross v is going to be pointing out of the plane, and you can actually see r crossed into v will indeed be in the z hat, in the k hat direction. And the fact that you divide by r squared has to do with the fact that, one, you've multiplied by 1r here, and then you also have to include the fact that velocity is related to angular velocity through a radius. That is, the further you are from the origin, for a given rate of change of the angle, the faster the object is moving. So in general, for a particle that's moving, omega can be obtained by taking the cross product of r with the velocity and dividing by r squared. The main reason why I want to highlight this right now is actually this sort of effect, this idea that there's a sort of cross-product relationship that gives you angular quantities based on linear quantities, is something that comes up again and again. So you've got angular velocity that depends on r cross v. You also have angular momentum. Angular momentum is r cross p, right? So angular momentum is the position vector crossed with the linear momentum. Torque is r cross f, So there's sort of an interesting analogy here that has to do with the cross product and the idea that you obtain these angular quantities by taking a cross product of the position vector, or the relevant position vector, with the relevant linear vector quantity, whether it's momentum or force or velocity. Now, there is, of course, an r-squared here. There is not an r-squared that's showing up down here. That has to do with the units and making everything work out. But we certainly could sort of expand that we could come up with a quantity that would make sense that was simply r cross v.